Okay, so let's now go back to SolidWorks to open the SolidWorks essentially. So we have, so this is what I already did last time. So let me just discard any of this. So you'll open the SolidWorks as usual, or you can just directly click on the part file that I have supplied, okay, to directly open the part file, okay. So the first step in this kind of analysis will be very familiar to you, which is basically to make your part geometry. Now, the actual finite element analysis can be done using various ways, right? You do not have to model the actual geometry exactly, because you can do the analysis, for example, in a 2D simplified manner or a 1D analysis as well. But keep this in mind that any of those will also then introduce some assumptions about the model behavior. But practically, we always take certain assumptions about the model, because no model can be a perfect replica of the reality, okay. Each model has a different level of simplification, and how much simplification you use depends on your computational resources, okay. So think about it. If you're trying to model a full aircraft, you cannot possibly model each and every component on it in a single analysis, right? So depending on what you are trying to get, it may be just possible to have a sort of a line sketch, 2D sketch sometimes, to get the first some main information about stresses and strains. Then you can focus on certain areas where you want to focus and do more detailed analysis, okay. So the type of analysis that we are going to do today will be a 3D finite element analysis, because that can be done quite easily in SolidWorks. But keep this in mind: if your part sizes will become larger, then this kind of analysis will become computationally very heavy. And although our lab computers are quite powerful, even they start to struggle. But not so much for this small part that I'm going to demonstrate right now, okay. So essentially, as part of this, I will show you some ways of, for example, simplifying the model, but then later I will also show you the effect of what we call as mesh convergence, okay. So what do I mean by that? Essentially, one of the fundamental reasons that you were not able to get the stresses correctly was because of the, you were considering the stresses to be uniform in certain region, right? The finite element analysis also has to make certain assumptions, okay. For the finite element analysis, the stresses will be uniform within that element, right? The values can change on the nodes, but as far as the within the element is concerned, it has to be either uniform or it has to be with a known function. So for example, it can be through a linearly varying function or some other thing like that, okay. So essentially that means then your size of element will also affect your result as far as the assumption of how the stresses are changing within that element, okay. With a software like SolidWorks, a lot of those details are actually hidden from you, right? So it's good for everyday use in industry. But if you are somebody who's developing these methods, then you really want to have something which is more powerful and gives you more flexibility, right? But I think for the purpose of this course, this will be perfectly fine, and I will be able to show you some change of the size as well as the quality of the elements to show you how those affect the results. Right. Yes, Ahem?
So are we going to draw anything or just
Yes. So essentially what I'm going to do is I'm going to use this part, and now I will go step by step through the analysis. Now, I have also uploaded this chapter of the book, okay, from which I have taken this example, and this is also available for you to use in this course on D2L. Please do not spread it. It is only for this course, okay. So this is same part, everything is same, but just the units are different here, okay. So I have done it in SI system, he has done it in the imperial system. Okay, so inch pound system basically. So
We can convert them.
yes, so I've just simply done it in SI for you. So it will be using, so you will be following exactly the same process and same steps, okay, as here. But first I will go on and explain it step by step in front of you as well. Maybe we'll not able to complete it, but then whatever portion I'm not able to complete, hopefully you'll be able to complete by following the steps in the manual. The version in the manual is slightly older, okay. So there is one little change that I will explain to you during the analysis. Other than that, I think most of the interface is still the same, okay. And it will be good for you to read through this chapter to get better, deeper understanding of what's actually happening in the background, okay. So let's now go through the process. So the first step, like I said, is to model the part. So once you have modeled your part, the next step is to simplify. What does that mean? In the model, many times there are details which are important from the point of view of, giving this drawing to somebody to actually machine, for example, right? But they're not too much important from the point of view of stress analysis, right? And having them included in the model, you can include them, but they're just going to make your model more computationally expensive. You understand the term computationally expensive? Meaning?
The computer takes more performance load out of the computer to calculate it.
Yes, you need more memory and you need more processor power.
Yes.
Okay? Why? So think about it. Like I told you that you are going to divide it into elements. So for this narrow region, you'll need to have much smaller elements as compared to the rest of the part, right? So firstly, meshing this region will be difficult. But secondly, even if it meshes it, it will, so let's say if in the original model there were 1000 elements, now because of this region you may unnecessarily need 2000 elements just because of these smaller regions which will have large number of many smaller regions to capture the stresses correctly here, okay. So that will increase your computational memory requirements because each of those elements will have nodes, each of those nodes will need calculations, right? So each of those data points need to be stored somewhere, right? So that's why the computational power will become more that is needed, and the storage will also be more that is needed, okay. So the first step that we are going to do is we are going to simplify the model, and then this is again something that will come through judgment or with the experience, that which parts you can simplify and which parts you cannot simplify. For example, in this case, if I try to simplify this notch, right, complete or eliminate this notch, it's going to completely kill the purpose of my analysis, right? So I'm not going to do that. But this outside portion, we'll see, will not have a large effect on the actual stress distribution in the part, okay? Because of the way how the stresses are distributed. Okay, so let's now do the simplification by simply selecting our features that you don't want. So I already have a group here called as fillet. So I will right click on this, and then I will click suppress. If you do not have a group and you are physically trying to select, then you can actually hover on it, press your control button and click on it, and you will be able to individually select each one of those parts that you are trying to remove from your analysis, okay. So I can basically select on all of these 8 fillets separately, right? And then I will basically just simply right click and I will click on suppress, and immediately you can see now that all my fillet features have been suppressed and my part looks more like the drawing I was drawing on the board, right? The drawing I was drawing on the board was like this, so it's more comparable to what I was trying to analyze there, okay. In this case, it's on the outer edge, it will not affect it significantly. You can try it running with and without fillet later for your own peace of mind, okay. But for now, I will run it in the simplified manner, okay. The justification is that these fillets are on what we call as a free surface, okay. So they will only affect the stresses very close to the maybe the constrained edge over here, but nowhere else in the model, okay. And even that is not going to be very significant. If anything, they will reduce the stresses, not increase them. So they are actually better for your model, okay, because of the smooth transition at the edge. Anyways, let's now run the analysis using the method that I'm just going to show you. So first step in this is to set up the simulation. So you will need to go on to the simulation tab. In my case, this is already highlighted, but if it is not highlighted, you can go and click on the simulation tab. In the simulation tab, you need to click on the new study option, okay? So this will bring up a menu that allows you to select the type of study that you are going to perform, right? So in this case, you can, in the SolidWorks, you can do several different types of simulation studies. The most commonly used one is the static analysis, basically, which is exactly the type of analysis that we have been doing in this course, okay? So that's the one that we will select. If it is not already selected, just simply click on this icon and it will select it for you. There are other options like thermal, buckling and fatigue and nonlinear and dynamics. These can also be selected if there is a requirement. When I teach you the machine design course, hopefully if some of you take it with me, then I will be covering the fatigue as well as buckling analysis as part of that course, okay? But here in this course, we will be focusing only on static analysis. The next thing is that do you want a 2D simplification or not, okay? We can do a 2D simplification, but because I'm trying to demonstrate to you this as a first example, I want to demonstrate it for a 3D case, and we will just not tick this box, okay? By default, SolidWorks has 3D as the default option. There are other softwares which actually have 2D as the default option, okay? So it depends on the software you are using, right? So then we will give it a name. This name can be really anything that you want, but for now, I will give it the name based on the names that I have given you here to record the data, because I have asked you to later on compare and record the data using these tables, right? So my force case is 26,650 newtons, and material for my case is AISI steel. So this is really for your report purpose. This is not going to have any effect on the simulation, right? And now I will call my first analysis. I will give it the name of the mesh that I'm going to use, and that is draft mesh default size, okay? Again, like I said, you can choose a different name, no problem. But I'm just simply using this name so that I can later know that which data to put where, okay? So once I put this name, I'll select on this green arrow to accept the settings. So I'll say okay, and this will now bring the part. So now you can see here, this lower pane on the left hand side shows you the simulation options, right? Your part is now appearing here, and it is giving you the part name as notch bar S2005 bracket 1, right? Now, in your case, if you don't have any, it may not have the bracket 1 there, okay? Right, first step. Now, in any finite element analysis, essentially, you have to follow a 4-step approach, okay? The first step is to make the part, drawing of the part and any simplifications related to it. So we have already done that now, right? And basically bring that part in and create a study. So this part thing we have done. The second step is to tell the software about material, okay? Because if you don't tell it, it will not know whether it is steel or it is plastic or whatever it is, okay? So you have to define the material. The third step will be to assign what we call as the boundary and loading conditions, okay? And then after that, you will have to do what we call as meshing or discretization. And then finally, you will submit it for solution and it will produce results. All of these steps up till meshing are called as pre-processing. The step of solution is called as processing, and then any analysis of the graphs afterward is called as post-processing, Okay. In old days, we used to have separate softwares doing all of these three tasks. Okay. But now things have changed. Software is much more advanced, so we can do everything in a single interface. Okay. But still, in big companies, if you are using some of the traditional softwares, which are very powerful, they may organize the things separately within the same software, but having different packages for each one of these. And there may be dedicated teams. There may be people who are just working simply on the setup of the analysis, and there may be people who are just working on the post-processing of the analysis for big parts. Right. So now how to assign the material is simple, because we are going to use a built-in material. In this case, I will right click on this part name over here, and I will click on apply edit material. Are you following me? So once I click on this, I get this window open, which shows me the option of the materials that are available in the SolidWorks. Now you can choose if you have, let's say, plastics, copper, rubbers, wood, steels. You can go there and you can browse, or you can just simply search for the material name. So in this case, for example, AISI, and it will bring you the relevant materials up, right? And then I know it is, in my case, it is AISI 1020, so I'll click on it. In many cases, you may not have the actual material in the library, or maybe the manufacturer that you're getting it from has a slightly different set of properties. In those cases, you can copy this material into the custom library and then edit the properties there. Right now, if you try to edit it here, it will not allow you to edit the properties because it is read only. Okay. So if you want to make any changes, you'll need to copy this material over to the custom material folder, save it as in a new library, and then it will allow you to save changes. So you can see here now very quickly it lists the properties. So like, for example, elastic modulus, it is listing as 200,000. That's why I use this. So in your case, whatever material is, go here and read the value of the Young modulus from this menu. This is what I was saying that I will show you later. Okay. Got it? So this is second thing that you'll need to know is the yield strength, because later on when we calculate the factor of safety, we'll use this value as well. Okay. So note down these values for your comparison later on. Now there are certain other options like, what type of approximation you are using. Are you going to use it as linear elastic isotropic, or are you going to use it as orthotropic? So orthotropic meaning that you have different properties in three different orthogonal planes. So it's used mostly for things like, reinforced composites, fiber reinforced polymeric composites. You have to use orthotropic set of properties. But for most of the steels and other metal alloys, you normally just simply choose isotropic material behavior. Okay. So internally, what now this definition of the material allows the software to do is to, I showed you that the matrix that links, all the stress components with the strain components through the matrix of the material properties. So this is precisely what it will allow the software to do internally. Okay. So with this now, I'll just say apply, and then I will close it. If the name of the material comes next to the name of your part, then that means the material has been applied correctly. Okay. In SolidWorks, the material application is on a part level. So if you have more than one part in the assembly, then you will have to separately apply the material to each one of them. Okay. Sometimes same part can have different materials in different regions as well. Okay. So again, you can do partitions and other things, but best is to then keep them as separate parts and then create an assembly, right, and assign the different materials. So like I said, SolidWorks has some limitations in terms of the analysis capabilities, but they can be overcome quite simply if you know workarounds. Okay. Now, once we have assigned the material, the next step is even simpler. We have to apply now the boundary condition, because look, if you do not fix it on one end, it is no longer going to be a static analysis, right? So you need to tell the software where it is fixed. So what I will do is I will just simply rotate it in a way that my x-axis is along, my YZ face is visible to me. Okay, because this is where I will be applying the boundary condition. So I'm basically going to constrain this entire face as well as the edges along it. Okay, so to do that I need to go into the fixtures. Now there are many types of fixtures depending on the type of connection. So for example, if you had a pin connection, you can just simply use it using the roller or slider type of connection, allowing it to move in one direction and be fixed in the other directions. Similarly here, right now we just want all of the edges to be completely fixed, so it's like a built-in condition. So I'll now go in this, I'll click on fixed geometry, and after clicking on fixed geometry I'll select the face that I want to constrain. Okay, I will also constrain these edges. Okay, so as to give a completely fixed condition. Now if I don't fix these edges separately, you may get slight changes in the local stresses in this region, okay, which is not going to be significant in our case, but it will give some differences. There are, like I said, other types of so all the faces that the faces or the edges that you have selected will appear in this list. Once you are happy with your selection, click on the green tick and click OK. And now these green arrows are showing you they are showing the constrained face, right? They are showing where the displacement is 0. So the way any finite element analysis applies these boundary conditions is that internally it writes this relationship F is equal to KU, where U is the displacement on each of the nodes of the elements, okay, and F is the force. So essentially this is then solved in a matrix form, where this will be the material stiffness as well as the geometric stiffness included in the K, and then it will solve that system of equations. So here on these boundaries the U value will be prescribed. Now the next step is to apply the load. When you right click on it, and because again you have got different types of loads that you can apply, in the next week we are going to use a torque that we are going to apply, but this week we are applying a simple axial load. So we go and we say force, and now I show the other face on which I am going to apply my force, and I click on this. You see, when you see the arrows, they are pointing inwards, meaning this is actually doing it in compression. So what I need to do, I need to reverse the direction. So I click on reverse direction. Okay. So for this, all I did was I went into the external loads, right clicked on it, selected force as my parameter that I want to use. Then I clicked the face on which I'm going to apply it, and then I clicked on reverse direction to change the direction. Next, I need to tell the software how much force is there. So it is 26,650 newtons. Okay, so this is basically the force that is being applied. And now it also asks me whether it is per item. Right now, because there is only one face selected, so it doesn't matter. But sometimes you can have more than one faces on which you are simultaneously applying the forces. Then you have to decide whether it's a total force or per item force. I'm now happy with my selection, so I'll again click the green tick, and there we go. So now the software knows the material, it knows where the object is fixed, it knows where the forces are applied. Look, this may seem very simple, but the thing is that even if for a very complicated part, these are essentially the same steps that you'll have to do, right? And if you do them right, your analysis will work correctly. And if you don't do them right, you have garbage in, garbage out, okay? Because the software in itself will not know whether you have set up the problem correctly or not. Right. Next step, as I said to you, will be discretization or meshing, okay? So meshing is the heart of your finite element analysis, because it basically creates those elements that will allow the software to then solve the problem. So you right click on the mesh and click on create mesh. Okay, when you click on create mesh, you have certain options here. You can see here the first box is showing you mesh density. Mesh density means that what is going to be the number of elements per unit length of this part, which will then indicate the size of the mesh itself. Again, because SolidWorks is built in a way that it's meant for very rapid use in the industry, you can see that changing the mesh density is just like changing the slider from on this scale from coarse to fine, and you will be able to change the size. You can actually see the effect on the size. This is going to be relative to the actual part size. So if you click on this mesh parameters, you can see here it shows you what the lengths are, what is how many number of minimum number of element in a circle will fit, and how, so some of those other parameters. So if you click on reset, it will put it in the default position. Okay, and with the default position right now for this part size, the element edge size is 4.27 mm. If I move it on a coarse scale, it will make it 8.55, but if I move it on the fine scale, it will make it 2.1. Okay, so for now I will just keep it on the middle, which is the default value. That's why I called it as default size. The second thing in the analysis which I said you to use was the draft quality. Okay, now the quality will again, there are different options. You have got blended curvature, you have got standard mesh, you have got curvature based mesh. Now again, a lot of this discussion needs more time, but right now you can just simply go for standard mesh. Okay, so you're not really applying any of the other more advanced mesh control features. So that's what you're doing. And secondly, what you're going to do is go into this tab of mesh quality. Now this is the only difference between the how the book is doing. I told you because of the version. So in the book, if I open up the page there, I can show you. So when you go down, you can see here it is asking you to click on this advanced button underneath the standard mesh option, and it is saying select draft quality mesh. Okay, so this is no longer there in this new version, right? In the new version, to do it, we have to go into mesh quality, and in the mesh quality, by default now SolidWorks keep it as high quality, but we will move it to draft quality for this analysis. Okay, now when I click on go back on the definition, I can see certain changes here. So all of the changes are there, so I can just simply click on OK. Now I will explain later to you that what is the difference between draft quality and high quality. Okay, but we'll do that slightly later. So now as soon as I click OK, the software does a bit of processing and it does this discretization of the domain for you, and you can now see the whole part divided into these wedge-like elements, right? So you see all of these wedge-like elements, and they are here. And you can see here that because of these wedges, the circular face is slightly approximated, right? It's not exactly circular, but depending on, of course, the number of wedges that will be here, you can have more closer approximation. Okay, so right now what you need to do is see what you have done. So you go into the mesh and go on to right click and go on to details. It will open up this box for you, and it will tell you that okay, you've got a solid mesh. The mesher used is standard meshing technique. You've got 16 points Jacobian, okay, for high quality, but because you have not used high quality, you have used draft quality, which will have fewer points for the Jacobian. Now what does that mean? Basically that means that, like I said, in the SolidWorks, I can draw it for you on the board. So when you are going to have these elements, right? So let's say this is one of those wedge type elements. So you've got all of these nodes. So the computations, the minimum that the software need to do is to do computation on each one of these nodes, right? But then for high quality, you can have more nodes somewhere here, for example, mid-side nodes we call them, right, on each of those faces. So it can be here, here, underneath here, or you can even have nodes over here for quadratic elements. For linear elements, normally we do not have the nodes on the middle of the edges. You only have the nodes on the vertices, okay? But even for the linear elements, you can introduce nodes on each of the faces. What it does is it increases the number of computational points again, and therefore allowing for more better calculations, okay, and better integration for the average results for each of these elements, okay. So that's basically if it was high quality, and if it was draft quality, it will be only mainly the edges. There are of course more mathematical detailed differences as well, but I don't think there you need to go into that. But if somebody is interested, I can give you, I mean, you can even look up in the SolidWorks help files. It gives quite a lot of the details about this. Now what I want you to note down is the total number of nodes in this case and the total number of elements. So the total number of nodes is 1606. So this is what you need to write down for your first case. Depending on your part, it may be same or slightly different. Yeah. So the difference will not be huge if the process is same, okay, for this part, because the part is same. And the number of element is 6444. So 6444. So you can see that the software is basically going to carry out the calculation for these 6444 elements on these 1606 nodes to solve this problem, okay. Now, so this is about the mesh. After this, what we need to do is we need to run the analysis. So to do that, you just simply need to go on to run this study, okay. And as soon as you do that, it will start solving. Maybe it will take a few seconds, and then it will produce a plot like this for you. So all I did was I went into run this study, okay, and clicked on this after that, okay, and it creates some default plots for you, okay. So our processing step is complete, our analysis step is also complete, and now we need to do post-processing. Now I'm not going to use all of these default plots that the software has produced for us. Rather, I will be plotting my creating some of my own plots, and I'll explain the reason for you. But I think to keep the video short, I'll just stop the recording at this point, and I will again record in a new video afterwards, and then we'll continue.